welcome. I'm Mike Smith. I'm president of the Friends of the School of Mines Geology Museum. And there's a little bit of a story about how this 2.5-day series of events came to be. A number of months ago, I make a long story fairly short. I encountered Dr. Hazen's mineral evolution and mineral ecology papers in the library in American Mineralogist here on campus. And as a result of reading citations and bibliography down at the Socorro Mineral Symposium, and I went and looked at the papers and read them and went, wow, and then went to Google and Googled Dr. Hazen and found him particularly all over YouTube and listened to several of his lectures and went, wow. And then thought number two was, we've got to get him to mines. So out of the blue, I sent this email off to Dr. Hazen and said, we have this lecture series of mines, by any chance would you be interested in coming? And seeing that he had keynoted everything all over the world, I figured there was a 50% chance that he would ignore the email altogether and a 50% chance that he would say, sorry, just way too busy. And about 3 days later, I got a nice little email back and said, boy, we are just incredibly busy, but however, since this is School of Mines, might be interested. And so that was step one, followed with another email, since we have a very small budget with Friends of the Museum, and this was what would you expect in the way of an honorarium question. And got this wonderful, gracious reply that said, well, how about instead of an honorarium, I bring a couple of some of my best postdocs out with me, and we can do some workshops and seminars along with the evening talks. And that was just a dream come true. And so anyway, that's how all of this started. And the geology and geological engineering department jumped in, and a number of other organizations jumped in. And the end result is what's going on right now. So in any case, in terms of financial contributions, if you like what you hear tonight and events like this, here are some membership forms for Friends of the Geology Museum. And also, I did a little single-page list of links for Dr. Hazen's, a few of his things, including his homepage and this wonderful 2008 mineral evolution paper in the American Mineralogist, his 2009 evolution of uranium and thorium minerals paper, also in American Mineralogist, the 2015 mineral ecology paper in the Canadian Mineralogist, and then basically bibliography and stuff about mineral network analysis and YouTube links. So I'll leave those up here. And as I said, there are a number of organizations that have jumped on board and are helping sponsor this. There's the School of Mines Geology Museum. There's Friends of the Geology Museum, my organization. There's the Arthur Lakes Library. There's the Mines Department of Geology and Geological Engineering. DREGS, Denver Region Exploration Geologist Society, has been very generous, and they've also organized several of the events here during these 2 days, and also the Colorado Scientific Society. So let's see, and in terms of things coming up, tomorrow at noon in the Betcher room in the library, Dr. Hazen, from noon until 1:30, Dr. Hazen is going to be leading a discussion of his book, Story of the Earth, and I understand there are still a few seats available on that, so if you'd like to turn up there. Luke, you've got a panel discussion tomorrow. Would you like to tell them about that?
Real quick, a significant portion of the focus of this two-day event has been on the application of some of the big data analytic techniques, visualization techniques, to minerals exploration. There was a workshop today, a seminar, followed by a workshop today, and there'll be a workshop tomorrow. And then at 2 o'clock sharp tomorrow, there'll be a panel discussion involving 8 panel members, representatives from Carnegie, from RPI, as well as representatives from industry, the government, and academia, addressing just that, the application of big data tools to minerals exploration. So that's open to the public. It's over in the Brown Building, room BB 280W. If you're interested, need further information about that, just get with us and we'll let you know. Encourage you. And in addition to the Friends of the Museum, which I encourage everybody to consider seriously becoming a member, dregs and the Colorado Scientific Societies are a real good buy for your money. And we'll encourage everybody who's not members of those organizations to think about joining them as well. Thanks.
Excellent. Let's see. Also tomorrow from 4:30 until 6:30, just shortly before Dr. Hazen's second talk in this room at 7, there's going to be a public reception over in the Geology building for Dr. Hazen. And I'm told there's finger food and stuff like that. And I'm also told there will be copies of Dr. Hazen's book, The Story of Earth, available over there at that open house, so that you all are welcome to come over there and eat whatever turns up, and then wander up here for the evening talk at 7.
Mike, it's at the museum, not the geology.
It's at the museum.
You're right. I'm sorry. It is at the Geology Museum. Okay, so that's end of commercial announcements and the official stuff. Let's see. So Dr. Hazen is senior staff scientist at the Carnegie Institution in their geophysical lab, and he's Clarence Robinson Professor of Earth Sciences at George Mason University, Fairfax, Virginia. He received bachelor's and master's at MIT, and while he was there, he managed to find time to also study trumpet at the New England Conservatory, and made a significant career as a symphonic trumpeter in the classical music field. Got his PhD at Harvard in earth science, 400 scientific articles, 25 books. He was the 2016 Roebling Medalist and former president of the Mineralogical Society of America. And the Roebling Medal, for those of you who don't know, it's basically approximately equivalent to the Nobel Prize in Mineralogy. And anyway, his recent research focuses are on the role of minerals in the origin of life, and also the application of big data to understanding mineral diversity and evolution. He's director of the Deep Carbon Observatory, which is something like 2,000 collaborators now.
50 countries.
Yeah, 50 countries. That was a $10 million grant, largely from the Sloan Foundation, and that's got another couple of years to run, and the odds are very good that it's going to continue beyond that initial grant. And so he's a marvelous communicator of science at both the technical and non-technical level, and so there is a great courses DVD set, I think it's 24 lectures, that parallels his book, The Story of the Earth, which is a good way to watch it in addition to reading it. And so without further ado, please welcome Dr. Ronnie Hazen.
It's such an honor and a privilege to be here at the Colorado School of Mines. This is a mecca for earth scientists around the world. It's known for its role in basically learning about, understanding, preserving, and finding our nation's resources. And so as a mineralogist, as someone who has, since I was 9 years old, loved finding, collecting, and understanding minerals, this is a great honor and a privilege. And I speak not only for myself, because much of what I'm going to talk about tonight is the result of early career scientists, an extraordinary group of people from several different institutions, people with backgrounds not just in geology, but in data science, in mathematics, in various aspects of the biosciences. And together we're trying to explore the coevolution of the geosphere and biosphere. We came here to try to understand and learn from your colleagues here about how perhaps big data approaches can be applied to the discovery of ore deposits. And 5 individuals in particular, Simone Runyon leading the charge, Shauna Morrison, Xiao Liu, Ahmed Alish, and Anirudh Prabhu are all with me. And in fact, they would be here right now, except for the fact that we had a workshop this afternoon. We were given some new data sets, and they're going to be working, we'll probably all be working all night, so that by 8 o'clock tomorrow morning, when we meet again, we'll be able to show you some brand new visualizations. So I know a number of, who all here was at the workshop today? A bunch of you, right? So our ambition is to show you first thing tomorrow morning the progress we made in various kinds of things called cluster analysis and network analysis and so forth. So this is, we just love this stuff, and we're very, very excited to be here to talk about it. A lot of the work we've done is available online. Everything we do is open access. And so I encourage you to go to dtdi.carnegiescience.edu, where you can look at some of the visualizations I'll be talking about, and you can meet some of the people, download some of our publications, and so forth. So tonight I want to cover 3 sort of broad areas where data has given us new discoveries about our planet through deep time and through space. First is called mineral evolution, and that's the study of how minerals' diversity and distribution have changed through about 4.5 billion years of Earth history. Second, mineral ecology, which is looking at the diversity and distribution in a spatial sense across Earth. And we'll see that Earth has a very special distribution of these mineral species. And finally, a very exciting new frontier area called market basket analysis, something you'll find out that you've all experienced, but it's never been applied to minerals and ore deposits. Now, tomorrow night, I'm going to talk about another really fascinating and exciting new direction. It's called network analysis, but you'll have to wait till then. So that's tomorrow evening. I guess it's here, right? It's here? Okay, good. So same time tomorrow if you're available, and it's a really fun topic. Okay, so why are we doing this? Why do we care? Well, there's some very fundamental reasons I think that are common to all people who love the Earth and want to study it. We're really interested in the diversity and distribution of minerals, but also rocks, of fossils, of ore deposits, all sorts of the productions that we find at or near Earth's surface. We also, many of us are in astrobiology and planetary science, and we want to compare different planets and moons. And we're really excited at the discoveries we're making that show that Earth, its rocks, and its life have co-evolved. And you'll see some of the evidence for that this evening. So, the first part of my talk is on mineral evolution. As I said, this is looking through 4.5 billion years of Earth history at how Earth's mineralogy has changed. This idea was introduced in 2008 in November in a paper, an American mineralogist, as was mentioned. I also wrote about it in this book, Story of Earth, in 2012. And I will confess that the story that I tell is a very qualitative one. But let me tell you that story first, and then we'll see how big data can put really quantitative meat on the bones of this idea. So, mineral evolution is a change over time in the diversity of minerals on Earth, in the distribution of the minerals that you find, and the compositions. That includes the trace and minor elements, which really do change fundamentally through 4.5 billion years. And also the sizes and shapes of minerals, something that when you go to a museum, you admire the beautiful crystal forms and the colors and so forth. Well, those actually change systematically through Earth history, something that has not been given much attention. These are all part of mineral evolution. We studied the upper 3 kilometers of Earth's surface because that's what's available for study. It's what we're going to be able to observe on other planets and moons, and it's also the part of Earth's surface that most likely interacts with biology. Now, we certainly could extend mineral evolution down to the mantle, down to the core, think about Earth's changes in those domains as well, but for the time being, we have real data
or the upper part of Earth. I have to take a break here. I have to pause and defend the use of the word evolution, because we have been, in a few circles, questioned, perhaps criticized. They say evolution, no, you can't use that word. That's a biologist word. It's not a mineralogist word. And we disagree. For more than 100 years, geologists have talked about the evolution of igneous rocks. Norman Bowen, who was my predecessor at the Geophysical Laboratory. But also we talk about the evolution of planets, the evolution of meteorites, evolution of stars. So it's no real difference talking about the evolution of minerals. It does imply that over time there is an increase in complexity, a diversification of minerals through time. It also implies congruency. That means that each stage of mineral evolution follows logically from the one that came before it. That's true of all evolving systems, but it's not this. And so I want you to put this out of your mind. It's not Darwinian evolution. Crystals don't evolve. Okay, so the main core idea of mineral evolution is that new minerals arise through physical, through chemical, and most importantly, surprisingly, biological mechanisms, processes. This idea in 2008 appears to have been new, which is really a surprise to most of us in mineralogy, because it's not as if we hadn't thought about minerals as having ancient roots and so forth. But to give you a sense of why it somehow struck a new chord, we can't find any mention of this question anywhere in the literature before 2008. And how strange is that? Because if you think about it, in almost any field in which there's a history, you ask about the first. The origin of life, the origin of planets, the origin of stars, the origin of the universe. And so why would not mineralogists ask what was the first crystal in the cosmos? A mineral, after all, is a crystalline compound with a fixed structure and a fixed composition, and that combination of structure and composition gives you a mineral species. So what was the first mineral
Quartz.
in the cosmos? Good guess? Oh, okay, someone's read this. Giving away the punchline. So this is how we think about this question. You think about 13.8 billion years ago, the Big Bang. And so the story goes, the universe came into existence at a point, all the mass, all the energy, and the volume just kept expanding, so it was an increase in volume. And so things cooled, but it was much too hot for there to be any crystals. Indeed, there were no atoms at the beginning. It took hundreds of thousands of years for there to be an abundant supply of hydrogen and helium. And those are, after all, gas elements, so they're not going to form crystals. And so, what was next? Well, let's see, the gases come together, they're attracted by gravity, they form large stars, but stars are much too hot to have crystals. So, when was the first crystal in the cosmos? So you have to have a mineral-forming element, and it had to be cool enough that those elements were going to condense into a solid phase. And I'll give you a hint. Think about a star that explodes, or a very energetic star where a large amount of its gaseous envelope is ejected into space. It's going to cool, and these stars are indeed carbon-rich in their envelopes. And so, as you said, the very first mineral was diamond. It forms from a very abundant element in the cosmos, and it forms at 4,400 Kelvin, which is the highest temperature for any of these common elements to form a crystal. And you cool a little bit more, about to 4,000 Kelvin, and graphite becomes a stable form. So those are the first two minerals, and in fact there are about a dozen altogether, all very, very high temperature, what we call refractory minerals, things that form above 1800 Celsius or so. So really high temperatures, form from the most abundant elements in those stars. We call these the minerals. They're found today in the pre-solar dust grains, these microscopic grains that predate our sun, our planets. They came from the previous solar nebula. And they have about 10 essential elements, things like carbon and oxygen and nitrogen and silicon. And so maybe you could say the question of mineral evolution is, how do you go from a dozen minerals with 10 essential elements in the early stage to what we see on Earth today, which is over 5,300 minerals and 72 different essential elements? That's the question of mineral evolution. And we tell that story in a series of stages. I'm going to tell you about 10 stages of mineral evolution. So imagine that before the sun, before the planets, what you have is a great nebula of dust and gas. And some perturbation, perhaps by an exploding star, starts concentrating and coalescing some small volume within that nebula, but that's going to be our solar system. And it collapses inward, gravity, it starts rotating, it starts spinning on an axis. 99% of the mass goes into that central sun, it's starting to form, it's getting larger, it's getting hotter, compressing, heat, maybe nuclear reactions are beginning. On the outside, there's dust and there's gas. And that dust and gas is too tenuous to form anything through gravity. But you do have electrostatic forces, and so you get cosmic dust bunnies. The dust actually forms this very fluffy stuff. And then the sun ignites, or has pulses of energy called the T-Tauri phase. Or perhaps there's nebular lightning, and that lightning strikes, and it flash heats those dust bunnies, and they condense, and they drop down into little droplets, microscopic things called chondrules, and they become the building blocks of the most primitive meteorites, the chondrite meteorites. You can actually see masses of those droplets in many of the chondrite meteorites. So in chondrites, there are about 60 different mineral species. So we've gone from 12 to 60 in that first step. Then the chondrites, of course, start clumping together through gravity, and you make planetesimals, 10, 100, 200, 300 kilometers in diameter. They heat from inside through very short-lived radioactive elements. They also heat because of the gravitational energy that's converted potential energy. So you basically heat them. When you get to about 100 kilometer size, you start melting the interiors. You form a core that's metal. You form a mantle of silicates. That's stage 2. There are about 250 different minerals that we find today in meteorites that fall to Earth. And these include shock phases. They include high temperature thermal alteration phases. They include aqueous alteration, because many of these planetesimals will have a large amount of water that circulates inside. And so we see these different minerals. And so this becomes the building blocks of planets, stage 2. Stage 3 is when you form planets themselves. More differentiation, the cores grow larger, the mantle, and you start differentiating crust, light elements that move to the outside. You have a hydrosphere, you have atmospheres, so you start making things like clay minerals or hydrous minerals, maybe ices or salt type minerals. It all depends. If you have a very dry world like the moon or Mercury, we don't see how you can get much above 300 different mineral species. About 60 are known in the moon right now. And we don't think you're going to be able to increase that much beyond the 250 that occur in meteorites. Probably the same for Mercury. However, if you have a wet world, Earth is one of them early on. You can certainly get up to more than 400. We think that 420 is the prebiotic inventory on Earth, maybe 500 or so. The same thing for Mars. We think this may be the end point for Mars because it was warm and wet early in its history. And all the minerals that have been found on Mars so far fit this model. So that's stage 3. But Earth has other tricks. Because Earth's large enough, it makes, like all of the terrestrial planets, it makes a basaltic layer. That's that dense black rock, for example, what you see coming out of the Hawaiian volcanoes and the mid-ocean ridges. But when you heat wet basalt, partially melted, the melt has a very much less dense composition. It's silica-rich. It rises to the surface. It forms granites, the very core of the continents. In fact, what makes so much of the Rocky Mountains and gives you the high topography we have around here. And because those late-stage fluids concentrate lots of rare elements, here are some of them, exotic things like beryllium and boron, tantalum, the rare earth elements, and some other cesium and so forth, that you start making lots of other things. Many of the most beautiful minerals in museums, I love tourmaline and beryl and so forth, these occur. And it turns out that these complex pegmatites then form another stage. It gives you about 500 more mineral species, which gets up to 1,000. Now, it turns out the oldest complex pegmatites are not much more than 3 billion years, so it's not clear when stage 3, if that stage 4, stage 5, these all may be overlapping each other, as you'll see. But this is a way of getting mineral diversity. What the Earth also does is it initiates plate tectonics, perhaps around 3 billion years when it really got going. And plate tectonics gives you all sorts of interesting new minerals. You have new kinds of volcanism, so that you have new kinds of metals from there. Massive metal deposits, sulfides, sulfosalts, hundreds of new species here. Also, various kinds of high pressure phases, because plate tectonics pushes some crust down and bumps back up after it's been transformed by pressure, and so there's a whole bunch of high pressure minerals. This gets you up to 1,500 species. We can categorize very reliably that each of these following species could have formed by purely physical and chemical means. That's 1,500 species. But there's a problem here. On Earth today, we have 5,300, and the number is growing. We can account for about 1,500 of those by purely physical and chemical means. So the question is, what was the mechanism that formed all these other minerals, this incredible diversity that we see on Earth and not on other planets? And the answer is life. And if there is one punchline to the mineral evolution story that people remember, it's that, you know, Earth's mineralogy is a consequence in large measure of the biosphere. So this is an interesting point because many people who've worked on the origin of life, myself included, have resorted to minerals in the origin of life. You need certain minerals. You need them for various ways. You need minerals as protective surfaces. You make molecules, but those molecules can easily be destroyed in the harsh early Earth environment. So minerals protect them. Minerals select different minerals, molecules, left and right-handed molecules. They can pull certain sugars out of solution. You can do this selectively, therefore concentrate the exact molecules you need to jumpstart life. You can use minerals as catalysts to form essential biomolecules. You can use minerals as basically tiny particles of minerals that play enzymatic roles. They serve as catalysts in biology itself, and also they serve as templates to manufacture larger molecules from smaller ones. So we see that minerals can play many roles in the origin of life, but conversely, that life plays a huge role in the origin of minerals, and hence this idea of co-evolving life and rocks, in a very literal sense when it comes to mineral species and biological species. Okay, stage 6. Now life has been established. The earliest life forms are single-celled organisms called chemo-litho-autotrophs. Chemistry, rock, eat. So it basically means that those microbes are taking their chemical energy, the energy to survive, from chemical reactions on rock surfaces. They accelerate oxidation reduction reactions that would occur anyway. But because they can catalyze those reactions, they get a little bump of energy. Electrons literally flow through the microbes in the process of oxidizing or reducing surfaces. And so you get a new kinds of distribution of oxides, of carbonates, of phosphates, and other minerals. The game changer is stage 7. That's with the great oxygenation event, when algae began to really influence Earth's atmosphere and molecular oxygen became an abundant source of oxidation potential in the atmosphere. And so you form literally thousands of new minerals that form essentially like rusting, the oxidizing of surfaces. We can go through the list. There are thousands of them in terms of copper minerals. All of these beautiful blue and green copper minerals, which have copper in the most oxidized 2+ form, wouldn't have formed before the Great Oxidation Event, according to our calculations. For uranium, 90% of all uranium minerals, which have these beautiful colors, simply wouldn't have formed because it takes much too high an oxygen fugacity, a partial pressure of oxygen, before they can form. And before there was molecular oxygen in the atmosphere, there was no oxidant that would create these particular minerals, and thousands of other minerals. So we can go through the list. Any element that's sensitive to oxidation state, and many, many of them are, fit this category. So that's the Great Oxidation Event, stage 7. Stage 8 is a period of about 1 billion years when oxygen had been established in the atmosphere. The upper part of the ocean was oxygenated, the lower part was not, and we think of this billion-year period as when gradually the oceans are titrated, if you will, and they become more oxidized down to the base. There weren't a whole lot of new minerals at this point, although there's some really interesting tectonic activity. Nevertheless, this has been called the boring billion of Earth history. Well, also apparently, I'm told, was a very smelly time on Earth because of a lot of sulfur compounds in the atmosphere. Stage 9, snowball Earth. This is roughly 700 million years ago, where Earth went through a period of freezes and then hothouse events. During the extreme cold spells, some people suggest that the entire planet may have been covered in the mineral known as ice. So that was the dominant mineral for a period, and then the ice melted and you had a hothouse period when things ran away. It had to do with fluctuating levels of CO2 in the atmosphere due to rapid weathering of the continents, drawing down CO2, and then volcanoes still pumping out CO2 and building it back up. Finally, stage 10, this is the period of the terrestrial biosphere. It's when land plants first established themselves, also when animals came onto land. It's a period of biomineralization, where all sorts of new mechanisms created by biology to directly form minerals, carbonate shells, silica, apatite, phosphates, and other minerals that form only because biological activities precipitate them. It's an amazing saga, the things you can say about biomineralization. I'll just tell you one story. I love trilobites. I had a big collection. It's at the Smithsonian now, which you can see. But the eyes of trilobites, each of those little lenses is a single crystal of calcite, calcium carbonate. The calcium carbonate has a C-axis. It's a uniactive mineral. The C-axis is pointing at you. Now the trouble is, calcite is a terrible lens because it has what's called chromatic aberration. Red light and blue light separate, and so everything becomes blurry. But through evolution, which is an amazing process, these trilobite eyes are not just calcite, but they have a small amount of magnesium in them. And the magnesium is zoned radially from the center to the outside to correct for chromatic aberration. It's mind-blowing. Obviously, an evolutionary advantage to be able to see clearly, and so that's how the lenses came. And amazing animals, and you can still actually take photographs through some of those calcitic lenses. The formation of roots was another major influence on mineralization, because roots they break up rocks, they create clay minerals in abundance, an order of magnitude more clay minerals than had been formed before. There's the Rhynie chair, tiny 1 centimeter roots, about 410 million years old, but very, very rapidly as plants got taller, roots got deeper, and as root got deeper, plants got taller. So you had massive root systems as we see today, and this has really transformed the surface. It's done in a number of ways. One of the most obvious is, I say, the production of clay minerals, but also the armoring of riverbanks, so that rivers, rather than just sort of eroding wherever they will, with root systems, they have much more established channels. The formation of clouds through the activity of plants is well known, and there are all sorts of subsurface biota, including an amazing array of subsurface microbes that live, in many cases, many kilometers deep. Okay, I have told you a story. And like my book, it's a nice story, it's a pleasant read, it gives you, there's a beginning, a middle, and if not an end, at least we see where we are today, and maybe we can project to the future. Some people talk about stage 11 of the Anthropocene and producing all sorts of new crystals. Some people talk about problems ahead with change and so forth. But Earth has always changed, and Earth will not be disrupted by whatever humans do. We may be, but Earth will not. It's a story that, while it's ongoing, I think you can see the sweep and grandeur of our planet. It's a beautiful planet, and it does have a great story. But as a scientist, I have to tell you, it's sort of, it's qualitative. It's a story that doesn't have a lot of meat to the bones. And so, we want to be able to make this a quantitative story. And that's where data comes in. So in 2008, I realized, wow, we're going to have to work pretty hard on this. We're going to have to build a database. And so we did. I'm going to tell you about the mineral evolution work we're doing, primarily focusing on the first row transition elements. This group of about 10 elements that's so important, very common in the Earth's crust, economically important, plays. They're very sensitive to oxygen, so they played a lot of role in the redox history that I was telling you about. And also they play very important roles in biology, so they're interesting that way. So we wanted to study these. And so what we did is we built a database. So imagine this, 2008. This is the rough database. This is the complete list of all the known mineral species. I'll remind you again that mineral species is naturally occurring and has a well-defined composition and has a well-defined structure. And so right now there are 5,329, I think, approved mineral species by the International Mineralogical Association. And this rough database, you can go there, you can search by chemistry, you can search by structure, you can search by a bunch of things. I should tell you that the rough name was not our choice. Rough data is not a great name for a database. But it was funded with $5 million by Mike Scott, who was the founding CEO of Apple, And he said, I will give you this money, but you have to name the database after my cat. So Ruff the cat is immortalized in the mineral database. So what we did is we added this to Josh Golden, taking the lead for the last 8 years, Alex Pyre is a programmer, and an army of University of Arizona undergraduates who are paid $10 an hour to, by brute force, go into the literature, open it up, look for minerals, localities, and ages. We now are up to 160,000, which is getting large enough we can start seeing some systematic trends. This has to get into the millions. Ultimately, there's lots of dark data, hidden data. Mining companies have data that they won't release at this point. We need to change the data culture. But right now, this is how we're doing it. Brute force, 8 years and counting. But it gives us enough that we can start seeing some very systematic trends. And so here's 60,000 mineral locality age data for first row transition elements, things like copper and zinc and iron and cobalt that I just showed you. And you see through time, going from the now at 0 back to 4 billion years, the distribution. And there's some really striking things here when you start looking at it, and let me tell you about that. The first has to do with the supercontinent cycle. This is sort of a GIF file just showing the assembly of Pangaea, the last supercontinent when all the continents were together. There you see this big massive thing, but then they started breaking up. I know this is going fast. You see the South Atlantic, North Atlantic, and that's more or less our modern world now. So that is the supercontinent cycle, very, very fast. What we think has happened over Earth history, there have been at least 5 periods where the continents have more or less come together in a supercontinent, and then had a stable period, and then broken up, and then come back together. Those 5 episodes are extremely well documented in the ages of a very resistant mineral called zircon, zirconium silicate. It forms in all kinds of igneous rocks, and it's such a tough mineral that when the rock erodes, those zircon crystals just last forever, and they go to the next generation of sandstone and the next generation of sandstone. And so you can collect literally hundreds of thousands of zircon crystals, and because they contain uranium, you can date each individual crystal, and that's a cottage industry. And so you get graphs like this, and you see 5 big peaks corresponding to those 5 supercontinent cycles. In our work, we see the same thing, and while the data is much more sparse, and it's much more weighted towards the modern era where we have a better exposure in a lot of ephemeral minerals that are still preserved. In any billion-year period, like from 3 billion to 2 billion, the highest peak always occurs under the period of supercontinent assembly. And that's because when supercontinents assemble, the mountains are formed, they're crumpled up. So not only do you have mineral forming processes as the mountains are building, but you form a core of rock that preserves those minerals preferentially. And I think that's what we're seeing here. So tectonics is a big part of the story. But oxidation is also a big part of the story. And this is the biology half of the story. So think about copper. I mentioned copper before. It comes in its native form, copper in the 0 valence state, +1 or +2. +2 form is really pretty oxidized, so you're not going to see it as much early on. So Shauna Morrison and Simone Runyon have been working on a copper database, and they've colored this according to the oxidation state. So green is the 2+, and what you'll notice is that there's a much higher percentage of 2+ in recent rocks than in the earlier rocks. There's a lot more statistics I can show you, but that's basically just, you can see a change in redox through time, especially in the last 500 million years. Dan Hummer has been working on manganese minerals, which come in 2+, 3+, or the most oxidized 4+ forms. So very beautiful minerals. And once again, he's plotted these through time, back 4 billion years, and again, done statistics on it, and showed a very steady increase in the oxidation state of the average manganese mineral. So this is the kind of thing we can document. And as we get more and more data, we can see more and more details. For example, in the last 500 million years, there's a lot of interesting fluctuations in the oxidation state of the near surface environment. We can plot these then in all sorts of interesting visualizations. This is called a skyline diagram, which shows 4 variables at once. It shows the age, it shows 4 the different compositional variables, those 10 transition elements. It shows the abundance through time, and it also shows the oxidation state. And so while this is going past very fast, you can learn a huge amount studying this And it also points to different time periods when you're more or less likely to find ore deposits, I might say. We've now done this for the entire periodic table. This is online. You can get it from our dtdi.carnegiescience.edu website. Every one of these is a high-resolution PDF underneath each element. So you can look at Earth's minerals that contain each of these different elements and see what their temporal distribution is. This is constantly updated as well. And there are new kinds of visualizations. I'm going to show you a visualization that I got this morning. Our Australian colleagues at G-Plates, which is a magnificent web-based set of programs that visualizes Earth history through time, particularly plate tectonics. You can see how the Earth's surface moves. And on this visualization, we have plotted the appearance in time and on the right geographic coordinates of copper minerals in yellow and uranium minerals in black. So this is just the very first rendering done last night. So there's the view, and watch, and you'll start seeing mineral deposits popping up in various places. There's one in Europe, there's one along the North American west coast. South America is coming in, and you'll notice that most of the new mineral deposits are occurring in places where there's plate activity, either subduction or collision. We can see another view of the opposite side of the Earth. And so this is a G-Plates platform in which you can superimpose. Now, at this point, we only have a few dozen ore deposits. We can put thousands of ore deposits on this and see at what tectonic setting, at what time period, these ore deposits form. Furthermore, G-Plates can tell you for subduction zones, how fast was the subduction? How steep was it? What is the surrounding lithology? So if you're an ore geologist and you're looking for tectonic patterns to the emplacement of ore deposits, this is an incredibly powerful visualization tool. Okay, so that's the G-plate surrounding, and that's certainly something we're going to be working a lot more at in the coming weeks. Let me tell you one more story, because we see anomalies in our data. This is one that Xiao Liu, my colleague at Carnegie, has been working on. He's a geochemist who noticed when we were doing data on different plate tectonic periods that Rodinia is robustly represented in the zircon record. That's this supercontinent that formed about 1.2 billion to 1 billion years ago. That's the period where we see this very robust signal. But if you look at that data I showed you before, the 60,000 transition metals, they're all the supercontinent cycles. But look, Rodinia is just like a puny little thing. You'd think there should be, even with the erosional loss that you'd expect Rodinia to be much, maybe 10 times higher than it is there. Why is Rodinia so weak? And so Xiao started looking at the mineral record, and indeed there's the minerals of nickel, very, very poorly represented from the Rodinian period, whereas for the other supercontinents it's quite strong. But he found, whoa, niobium, there's a really robust peak for niobium. There's a robust peak for zirconium minerals, and there's a robust peak for yttrium minerals, which are all known as high field strength elements. They're a particular kind of element that concentrates in particular kinds of fluids. And he said, we need geochemical data. So what he did is he went to EarthChem. This is a different database, and it's basically the chemical information of rocks. You take a rock, you analyze it, and you can measure dozens and dozens of different chemical elements, their isotopes and so forth. He said, let's look at the different chemical elements through time in igneous rocks and see if we see a similar anomaly. What he found was astonishing. It's jaw-dropping. This is niobium concentration in igneous rocks through Earth history. It's representing about 100,000 data points, and that is a whopping peak at Rodinia. Rodinia is different. He did it for zirconium, and there it is, a whopping peak at Rodinia, which sort of correlates with the fact that we see a lot of zircons as well. And there it is for yttrium. It's also, by far, this huge peak. This is based on 100,000 data points. This is taken from all over the world and all kinds of igneous rocks. That's amazing. So if you look at cobalt, if you look at nickel, that's what we're seeing here. There's some fluctuation through time. This is the average composition. You see a general decrease because cobalt and nickel tend to concentrate in rocks that are called ultramafic and mafic, and there's a higher percentage of those early in Earth's history. So there's this gradual decline, but you certainly don't see this big anomaly in Rodinia like you did for yttrium, niobium, and so forth. So what could possibly happen? Either those minerals of nickel and cobalt and the other elements that are missing never formed, or else they formed and they've eroded away. And so this is what Chow has decided. He's looked at this. He said if you look at rocks of the age of Rodinia, for example, the famous Grenville province, which is part of a mountain belt that formed when two continents collided. Those rocks are unusually high grade, meaning that there's been tens of kilometers of rock weathered away, eroded away from that Grenville province. So Chow's conclusion is that what happened is there's this unusually high input for the high field strength elements because of a particular kind of tectonic setting that was different for Rodinia. But in fact, it was extremely high mountains that eroded away very rapidly that results in the loss of ore deposits. It isn't that the ore deposits didn't form during Rhodinian periods, they've all been eroded away and we've lost most of them. So that, I think, is a fascinating story, much more to be done, but it emphasizes that we now, with the data resources we have, we can be much more quantitative about the mineral evolution stories. We can see details we could never see before. And I think this is an incredibly exciting ongoing direction. It will play a very strong role in our understanding the distribution of ore deposits on Earth as well. Okay, part two, this is mineral ecology. Mineral ecology is the study of the diversity and distribution of mineral species across Earth today. It's a study of this spatial distribution as opposed to the temporal distribution. And so what we try to do is look at these distributions, and for this we are incredibly indebted to Jolyon Ralph and the community of collectors that crowdsource the MinDat.org database. There are 1 million mineral locality pairs from about 300,000 different localities around the world, and these are all available open access. You can go to MinDat.org, and this is the way we find out which minerals coexist with which minerals in which part of the world. I spent a lot of time, about 3 years ago, I said, I've just got to basically look at these minerals more closely. So I went to the Handbook of Mineralogy, I went to MinDat, I spent a week just looking at every single mineral species. Where does it occur? How does it occur? What are the ways it forms? And the thing that struck me right away was that, wow, most minerals are really obscure. You've never heard of them because they're rare. They only occur at 1 or 2 or 3 localities in the world. There are a few minerals that are really, really common. And then I was reading books on statistics, because I just had to say, well, how can we handle this? Turns out there's a branch of knowledge called lexical statistics. It's the distribution of words. And the distribution of minerals is exactly the same. So my mathematical colleague, Greta Heisted at Purdue University Northwest, applied these mathematical relations, because these books on lexical statistics are like this, and I can't get past the first 3 pages. They're written by people that are supported by largely NSA, because it's the analysis of texts and documents, emails and stuff. So that becomes very important because you can tell a lot about it. So here's the basic idea. Most words in a book or any document are common. A and the. Lots and lots of times they occur. But most of the words, the different words, are rare. They're used only once or twice. And those rare words define the topic of the book. They define perhaps the authorship. If you've got a rare manuscript and you want to say who wrote this, you can sometimes do lexical statistics and tease out the authorship. So here's how it works. This is a plot called a frequency distribution, where on the horizontal scale is the exact number of localities where a particular mineral species occur. So there's 5,300 different points on this graph as that, and then there's this probability here. And so there are a few minerals like calcite that are extremely common, but only one mineral probably occurs at 25,328 localities. And similar, cinnabar, a couple of thousand localities. Diamond is fairly common, 700 localities. But the rare things like Bob Downside have exactly 3 localities. 8% of all minerals are known from exactly 3 localities, and fully 22% of all minerals are known from only a single locality. Hazenite is known from Mono Lake, and that's it. By the way, it's microbial poop that occurs only seasonally when they have a dry season at Mono Lake, and the phosphate levels get so high the microbes can't stand it, so they excrete these little beautiful crystals. But it is microbial poop, my friend Sean Solomon says. Hazenite happens. I just live with it. So here's another way of representing that. It's on the vertical scale. 1 locality, 2 localities, 3. Black is the observed, the number of species as of when we did this in 2015, so a little over 1,000 species from exactly 1 locality. About 600 from 2, 400 from 3. In red is the model. It's a pretty good model. It's called an LNRE distribution, a large number of rare event distribution. Classic mathematical model that people in applied math would know about. And what it allows you to do is something really neat. It allows you to make an accumulation curve, predict the number of missing species. And here's how it works. Because of that model, you can say the probability when you go to a locality, so this is the number of mineral locality data. Remember, we're up to about 1 million now. When we did this study, it was 650,000. And we had about 4,900 species then. On the vertical scale is the number of approved minerals. And so if you go to a new planet you've never been to before, you start collecting. When you start out, the first thing you pick up is a new species. The second thing is probably going to be a new species. Maybe the first several. You'll find them really, really fast. But as you find more and more specimens and look at them, you say, oh, I've already seen that one. So the curve starts curving over. There's the data we have as of February 2015, 650,000, 4,937 minerals. And you can extrapolate out and show that there's at least 1,500 mineral species that need to be described. By the way, that's where we are today. We're right on the curve. So that was satisfying. There are good reasons to believe that the curve will actually not level out this fast. The technical reasons, so we think there could be a lot more than 1,500 species. But it shows that there's still a lot of work for mineralogists to do, which is exciting. What's more, we can tell you what minerals are missing, because you can do the same kind of curves for subsets based on chemistry. Here's the carbon mineral curve. There are 400 some carbon mineral species. We can do that nice frequency distribution. We can do the accumulation curve, predict that 145 carbon minerals are missing. And then we add other elements, carbon plus oxygen in this case. And so we predict that 135 of the 145 missing carbon minerals are carbonates or oxalates. So they have carbon plus oxygen in them. And then we can predict, I could go on and show you some of the specific predictions. But what we did for fun is we published this. We said, here's a list of missing carbon minerals that might be found on Earth. And then we started the Carbon Mineral Challenge. And this is an international effort. There's about 30 senior advisors from around the world, famous mineralogists and collectors and serious mineralogists around the world have been looking for new minerals. We have about 15 new carbon minerals so far. These are 2 of them that we predicted specifically in the paper. They're listed in tables that had not been found at the time we described this. We didn't predict everything. We predicted, for example, there'd be 8 new organic minerals, but we did not predict tenunculite. You may understand why when I read you the description. Tenunculite only exists when the excrement of a falcon bakes in the hot gases of a coal fire. So while we didn't predict that, at least it fits in the model of an organic mineral. And so this is part of the wonderful thing. By the way, about 50% of all new minerals that are found are structures that have been unknown to science, so you couldn't predict them in that sense. So there's a lot of new material science to be learned from discovering new minerals. Okay, so we can employ mineral data in this really exciting way, predict new minerals, things that are missing deposits, perhaps using the same sort of thing. So mineral ecology has become a really exciting field. By the way, this also works in paleontology. We were able to show, for example, the lower Jurassic ammonites. I asked my paleontologist friends, what percentage of all the ammonites that ever lived on Earth are in fossil collections in museums? And they would say, maybe 1%, maybe 10%, because there's this idea that the fossil record is really incomplete, about that. And so we did these statistics. It turns out that 85% of lower Jurassic ammonites have been discovered. Now, that has profound implications for evolution, because if 85% discovered, then you can't call on the fossil record to say, oh, it's so incomplete, there's gradualism, there's just this gradual change from one species to another. No, it looks like punctuation has to be the name of the game in paleontology. I think I'm not a paleontologist, so I leave it to the paleontologists to fight and struggle over this, but I think this is going to be a really exciting direction, and that's the kind of thing we're thinking about. Okay, part 3, market basket analysis. This one's short, but this one's really profound. So, what I want to do is I want to predict where I can find my favorite mineral, gillespite. I want to be able to say, Where's a place I can go there that's never been found and find it? You know, or what about if you have a favorite locality? Is there any statistical method you could use to predict what should be there, but you just haven't seen it yet, or you just haven't collected it, maybe it's just been overlooked? And the way we want to do this is something called market basket analysis or affinity analysis. It's a modeling technique. It assumes that you have lots of members of a set, and in this particular case, you're more likely or less likely to buy something because you've got a previous history of buying things and other people have previous histories of buying things. And you've all had this experience. You go online. I wanted to buy Jonathan Laney's astrobiology book. There was only a used copy, it was $300. I decided not to buy it, but within a second I got this. You're also going to like, and who knows why they said I was going to like John Horgan's The End of War. I mean, I despise his book, The End of Science, so why I would like his book, The End of War, I can't imagine. I mean, but they have reasons for doing this. And what it means is basically they have records for hundreds of millions of people, their buying habits, what they like, what they did, you know, the number of stars you give things. And even though it's a very sparse data set, because none of us buys more than, I suppose at most, a few hundred books, and there are 50,000 books. If you have hundreds of millions of people, you have the data you need to make these predictions. And the exact same thing can be applied to minerals. Because you have 5,300 minerals. They coexist with some things, they don't coexist with other things. Sometimes they always exist with a mineral, sometimes they never exist with another mineral. You have all that information. And so you not only have pairwise information, which is sort of the most obvious thing to check, but you have this much higher dimensional data that can be analyzed using affinity analysis. And so you could say, you know, I've got these 10 minerals at this locality. They always are found with this 11th, 12th, and 13th mineral. You can go and you can find them. I think this is going to happen. Here's how it's going to happen. You're going to put on your virtual reality glasses, and you're going to be able to go into some kind of visualization of the data, perhaps network analysis that I'll talk about tomorrow. You're going to say, oh, I want a computer, I want to see more about Gillespite. Show me Gillespite, show me specimens of Gillespite. Let me walk around virtually some of the localities where Gillespite exists. Computer, show me all the other minerals where Gillespite is found, also exist. And then you say, computer, tell me where I should go to find the next Gillespite crystal. And the computer will tell you there's an 85% chance that if you go to this locality where Gillespite has not been reported, you will find it there. This is going to happen. It has already happened. Jolyon Ralph at Mindat got so excited about this that he started doing this just based on the simple mathematics of pairwise coexistence. And he basically looked at one locality, Crooks Peak, New Mexico. Maybe somebody here has been there. I don't know much about this locality. Yeah. And he said, based on all the minerals that had been identified there, wolfenite should be present at that, but it had never been reported from there. It was not in any collections. And they went there and they found wolfenite. So that's a simple example. It's sort of an obvious example. It is data-driven discovery, but it's not the most profound example I could give you, but it's the first one, and it presages something. This is inevitable. It will happen. In 10 years, this is the way people will be discovering new minerals. It's the way people will be discovering ore deposits. Get data scientists on your team now, because it is happening so fast that it's inevitable. How long it takes? It's going to take a lot of creativity. It's going to take a lot of hard work. What we have to do tomorrow in our workshop is start building a big database. It may take 10 years to do the database we really need, but that's how exploration is going to happen in the future. Okay, so what I hope I've shown you is there's large and growing databases. These resources can be used in a variety of ways to understand the change of minerals through time, the distribution of minerals through space. These are just examples. There are many, many, many others that could be applied to earth and life sciences to try to gain knowledge about the future. I'll tell you some more about that tomorrow night when we look at network analysis. But this is an incredibly exciting frontier. I'm so grateful to all of you to be here tonight and to give me the opportunity to share some of these ideas. So with that, I ask you to please visit our website, dtdi.carnegiescience.edu. You get to see a lot of this information and open access resources of various sorts. I want to thank the people I work with. There's a network of the people who work on networks. And thank my funding agencies, and thank you all so much. Maybe there'll be even some time for a few questions. Thanks. Yes, please, let's start.
Well, historically, we can sort of a crude market investment approach by looking for pathfinders.
Yeah. Yeah, this is certainly the market basket approach, but I would say Pathfinder is sort of like the early days of Amazon. And you may have heard this story, but it's worth repeating. Early days of Amazon, they hired about 20 people to read book reviews and match up books to buyers. If some buyer bought 2 or 3 books, they would actually manually recommend the books to the buyers. And at some point, I don't know if it was Bezos or somebody brought in a data scientist and said, okay, you try it your way. And they applied affinity analysis. And the one data scientist sold on average 66% more books using affinity analysis, because a lot of the things are not intuitive. It has to do with likes and dislikes and subtle effects, and maybe you've had this spectrum of books that you've bought, and someone has another spectrum of books, and you start, as I say, the data is sparse, but if you have hundreds of thousands or millions, or now hundreds of millions of people doing it, there are trends in the data you just simply can't recognize just by using intuition and hunches. And believe me, I know field geologists who are incredible. I've known prospectors who could just sniff out, and they were using multi-dimensional thinking, but we can do so much more right now. I just feel like it's time to move beyond that. It means creating huge data resources that could have 100,000 or localities that are barren, and all their parameters. And tomorrow we're going to start our workshop by listing all the different fields that might be significant. There could be 1,000 different fields, just like 1,000 different mineral species and many, many other things. And the data is going to be sparse. In some locality, you're going to have a little bit of geophysical data. Some locality, you're going to have mineralogical data. Other localities, or you're going to have as a drill core of some sort. And yet, you put all that data together, just like this, and it's going to lead to discovery. Okay, you were next, I think.
Well, so the first land plants are usually put in early Paleozoic, mature.
Yeah.
Also has arthropods in it too. I remember a couple of years ago there was a paper with some weak evidence of land plants maybe in post-snowball, late Precambrian. Does your data at all weigh in on that?
We haven't weighed in on that, and I think the paleontologists could probably do statistical analysis of this sort. Maybe you can say, I've never thought about projecting how far much back. So say you can demonstrate we have 10% of the land plants that ever occurred on Earth. What's the probability that we're missing land plants from a much earlier period? That's an interesting thought. I've never really done that, but we haven't addressed that question specifically, but it's, that question, I gotta write this down. That's a really interesting, it's leading to a very interesting idea. Yeah, somewhere there were questions.
So it seems like on the one hand, there's a good number of serious mineral collectors who are studying rare material and probably finding new species that don't have the instruments or the facilities or knowledge to describe them. And then on the other hand, I've met some researchers who are studying weird rocks and say, well, I probably found a new species, but I don't want to bother describing this because it's a lot of work and I'll end up with a paper that's low citation or whatever. How do we make it more appealing to researchers to describe new minerals?
Well, there are researchers who are so passionate about this. Camp in California, for example, there's Christie in Australia, there's the people at the Smithsonian. So there certainly are plenty of places. In Arizona, they just described 20 new species in the last few years. And in Russia, there's just a flood of new species being discovered. So there certainly are places that are very, very excited and passionate about doing that. Collectors who find, the very sophisticated collectors generally link up with a professional someplace who can do the accreditation of a new species. So I haven't sensed that there's a huge gap in the ability to get new species described. There certainly are many, many more species. We've done some sociology of mineralogy studies where we calculated how many species are missing. If you look at a mineral, an element like tellurium, because there's been a lot of focus on it, we think only about 10% of tellurium minerals remain undescribed, at least based on present. But if you look at sodium minerals, it's closer to 40 or 45%. That's because sodium is not economically important. Also, it very commonly forms white, crusty, poorly crystallized materials that look like all the other sodium minerals, and they wash away every time it rains. So we've predicted several specific new species that should be found at Lake Natron, which is an alkali lake that has lots and lots of salt flats. You know, they're all sort of white, crusty crud, and there's going to be new minerals in those. It's just that it takes, you have to, if you know what to look for, you're more likely to find it. I'll put it that way. Please.
Missing minerals, presumably you can supply the missing chemical formula for a given one of those. Can you also supply the physical properties, color, hardness, crystal structure?
We have in the cases where either there's a synthetic analog, and a lot of the predicted missing minerals are things where we know the synthetics just from studies of phase equilibria. Or if there is a structural analog, for example, there are many minerals in the malachite group. You know, there's copper varieties, and there's iron varieties, and cobalt varieties, and so forth. And you can just basically say, well, what if you substitute this element for the other one? And you can sort of assume. And then you've got to, because you have a continuous series of different minerals, you can sort of estimate what phase it might be. But as I say, about half the new minerals that are discovered turn out to be structures completely unknown before it, so you can't predict those that I know of. I mean, there are certainly ways of predicting unknown structures, but these are ones that people haven't tried yet. Please.
Do you think volcanism is a sufficient mechanism to form the hydrosphere?
Well, to form a hydrosphere, you need to have a planet that's rich in volatiles to begin with. So clearly you needed to have some kind of inflow, you know, whether it's carbon-rich meteorites like carbonaceous chondrites, whether it's cometary type material and so forth, where there's lots of ices that got incorporated in the mantle, and then, or this idea that maybe there was a late veneer, a late bombardment, which brought in the hydrosphere from space. And I've seen arguments for both. I'm not enough of an expert to argue one way or another. Certainly volcanism plays an incredibly important role in all the volatile cycles right now, because you have subduction taking volatiles down. Volcanism brings them back up. What's not clear, and what's a really fascinating study is, particularly in the carbon cycle, I'm part of this Deep Carbon Observatory, and there are a couple of new mechanisms that are subducting carbon into the mantle that didn't exist before. One is about 200 million years ago, the invention of something called planktonic calcifiers. These are microorganisms, and you've probably seen the White Cliffs of Dover. That if you magnify them, you see these tiny, tiny little coccoliths. They're just amazing. Well, that's calcium carbonate that is now being formed in the middle of the ocean. Before 200 million years ago, calcium carbonate was only formed in the margins. So now there's much more calcium carbonate, and for 200 million years that carbon has been subducted. Furthermore, it's a cooler geotherm. It's not as hot, and so more of the calcium carbonate that gets subducted likely continues down and goes into the lower mantle as sequestered. So for the first time in Earth history, it appears, if you do all the calculations, that the net carbon budget is negative at the surface, that we're sequestering over a period that may be 300 to 400 million years. The equivalent of all the carbon at Earth's surface is going to get subducted. That's one extreme idea. So you really need volcanoes to help bring some of that carbon back up, and that's a major source of CO2 right now. Yeah.
Does that imply that we'll have another snowball Earth?
No, not at the rate that because if you take all the volcanic emissions on Earth, the annual emissions are a tiny, it's 1/100% or something, or 1% of the human emissions right now. So volcanoes are huge point sources. Mount Etna is large a point source as the largest coal-burning power plant, but no, the burning of fossil fuels is orders of magnitude greater than anything the volcanoes are doing. So that's the story right now in terms of the carbon cycle at the surface. Yeah.
Pharmaceuticals have a big interest in mineralogy and crystallography of their compounds. Do they have similar techniques, or have you learned much from the pharmaceutical industry that links into the kind of analysis you're doing?
So that's a terrific question. There is something called the materials genome that's being produced. That's a big data network approach towards materials discovery. I'll show tomorrow night some approaches to looking at protein structures and their variation using these approaches. It's not something I'm a real expert in, but the materials, look, there is not a field of human endeavor that involves some amount of data that's not being influenced by these new analytical and visualization approaches. It's everywhere. Geology is really late to the game in this. And it basically represents a huge opportunity right now. Say the opportunity will not be here 10 years from now because people will have already figured it out. But right now that's the sweet spot for making discoveries. So I feel very fortunate to be around and watching my early career colleagues who really understand this work. They're from the generation that shares data, and they understand the power of data. I use Waze now. I mean, Waze doesn't work unless everybody turns on their cell phone and lets you know where they are, and then you can figure out the traffic patterns. The unintended consequence of Waze, by the way, is that it's now causing traffic jams. Because so many people use it, they all take the same alternate route. So anyway, that's something that'll work out, I'm sure.
Much of what you've shown has to do with the distribution of mineral phases, for example, worldwide. Any thoughts or issues as it relates to, let's say, that the explorationist who's focused in a particular district? His world is that, and he's dealing with database from...
Same approach. These techniques can apply to a small region, they can apply to a state, they can apply to a country, whatever geographic boundary you can apply to a particular geological terrain. I think that the data techniques, even though the specific data sets may be different, but the analytical and visualization techniques are transferable from one problem to another, which is one of the great powers of this.
Do these techniques become less robust as you decrease the size of your database, which is what happens?
This is the question is about the size of data, and sometimes in the past I've kind of hyped this as being a big data talk or something. It's not big data. Geologists don't have big data. Unless you're sort of a seismologist or you have some kind of satellite that's monitoring something 24/7 for tens of years. People who do genomics, they have big data. The astronomers have big data. What we have is mid-sized or small data. The thing that's interesting about that is it turns out we have to work with data scientists. And they do not think of themselves as doing service work for the geologists. They are scientists in their own right. And they are incredibly excited by the new frontier of small data and mid-sized data, where you need various kinds of Bayesian estimation, other kinds of statistical techniques that have not been applied. Facebook doesn't care about that because they have a billion users, and so the noise out here doesn't matter to them. When you have data that looks like this, and that's your data, you have to be worrying about statistical significance and errors and all, and that's something that our data scientists that's how they're getting their thesis, that's how they're publishing papers, because they're doing the data science side of working with these modest-sized data sets. We're going to have to modify some of the classic techniques for these smaller-sized data. Now, of course, eventually we hope that we are big data. I mean, if we had 100 million localities with all the each with 200 geochemical trace element and isotope values, that would be a big data problem, but we're not there yet. Even a 5,300 mineral species coexisting with the other 5,300, so that's a matrix of 5,300 by 5,300 with all the metadata running out into a third dimension. That's not big data. It's sparse data. And sparse data is a different challenge. Thank you.